Good morning or afternoon or whenever you're watching this. This is mainly for the students undertaking Unit 21 of the High National Diploma Level 4. If it's any use to anybody else, fantastic. But that's mainly what I'm tailoring this to, and that's what the learning objectives come from. Now, in the last lesson, we looked at transformer theory. And what we said was that a transformer is some sort of core, and we looked at all the different makeup and the way that these things are built. But generally we draw them as a square core, and these things are usually 3D. So like that. Like that. And we normally have a set of coils on either side, at least one set of coils on either side. Now, the side connected to the power or the supply power is normally called the primary side. Don't fall into the trap of thinking, well, the one with the high voltage is the primary side, the one with the low voltage is the primary side, because depending on whether it's a step up, a step down, or even a buffer transformer, that will change. Now, the secondary side is normally the side connected to the load, and we call this the secondary. Now, on the primary side, we've got a primary voltage across that coil, and on the secondary side, we've got a secondary voltage across that coil. We've got a primary current, and I'm just going to draw that going in this direction for now, simply because I need to give it a direction. It's, you know, it's AC, so it will change directions. I totally appreciate that, but we've got to have some sort of direction on there. So we've got our IP for current primary, and coming out, which is the reference to the directions must be the same. We've got IS as well, which is the current for the secondary. And the last thing I need to note is we've got the number of coils here, and the number of coils on the primary, you've guessed it, is called NP, and the number of coils on the secondary is called NS. And the ratios go, the voltage on the secondary divided by the voltage on the primary equals the number of turns on the secondary divided by the number of turns on the primary equals the current flowing through the primary divided by the current flowing through the secondary, like that. And if you'll notice, it's VS over VP here, but IP over IS. And that's because these guys have got a inverse proportionality. So as this one increases, the current will decrease. And in fact, it's proportional. So if the voltage output doubles, the current output halves. If current output triples, the current output goes down by 2/3. So that's what we did in the last lesson, and we looked at some configurations of these things where we said, well, we had a voltage supply, a number of turns on the primary, and the current coming out, work out IP or VP. So that's kind of where we went from there. What I want to have a look at this lesson is a little bit of calculation. So we're going to do Cartesian, which I'm going to note down as cart, and polar, which I'm going to note down as pole. Now, Cartesian, as you remember from your electrical principles lessons and things like that, Cartesian has a real part plus J imaginary part. And your polar has, it's normally a little z like that, which is a magnitude at an angle of something. Now, the reason why we've got A plus JB here is it's all because of a phase shift between them. So if we say this is the J column and this is our real column, this number here, our A, will go somewhere on here. But our B, because it's JB, or you might have called that BI in maths, goes on the J thing. So they're actually phase shifted from each other. That's why you can't just add them together as you would two normal numbers. Right, so it's just a recap. I'll put some links down below for you to have a look at if you want any more revision on this stuff. And our polar is essentially a length. This length here at an angle of, and actually you can put these two together that they can exist on the same graph. So put our J there, our real there, and if we say that our B is there and our A is there, then what we do is we take an imaginary vertical line and an imaginary horizontal line. I don't know if that's picking up on the camera or not. And you essentially form a rectangle. It should be drawn a little bit better than that. I'm doing this freehand. And if we join up the bottom corner and the top corner together, again, you would normally do this with a ruler. That length there is the equivalent Z for this. And that angle there is the equivalent theta. So these two things are quite closely related. And obviously the maths behind that, which we'll come to in a second, is reflective of that as well. Now, you might have come across this in maths, and we used to, well, we still do, there's no used to in it. We still do call this trigonometry, or trig for short. And you use things like sine, cosine, and tangent. Okay. Now, if I wanted to convert between A plus JB and Z an angle of theta, what I would need to do is I would need to appreciate that this here is a triangle. All right, so I'm going to redraw this on a separate sheet. So we've got our triangle. And remember, in trigonometry, or trig, we'd call this side here, wherever the angle is, sorry, we call this side the adjacent. And because this side's opposite, we call this the opposite. And because this is the longest side, this is called the hypotenuse. This is all coming back to you now, brilliant. And what we need to do is, essentially, we need to take, if you remember, our opposite is our imaginary, our adjacent is our real, and our hypotenuse is our Z value. Okay? So I can rename these as real, J, and this one would be Z. Like that. Now, if you remember in maths, to convert between adjacent and opposite to the hypotenuse, we use Pythagoras' theorem, and that states that the hypotenuse squared is equal to the adjacent squared plus the opposite squared. Then, of course, we can simplify that down a little bit by saying that actually the hypotenuse is equal to the adjacent squared plus the opposite squared. And to get rid of that square on that side, we just square root the whole side like that. Okay, and that will give us our Z. Because remember, our Z and our hypotenuse are the same thing. The next thing that we're going to do is we need to work out this angle here. Right? Now, in something I must mention as well, sorry, this J is also called the imaginary number, IM, JIM. So we've worked out our hypotenuse, we worked out the length. Now we need to work out this angle here. So what we do is, in trig, we would say that the angle, it's that angle there, is equal to tan to the minus 1 of the opposite over the adjacent. But in this case, we're not using opposites and adjacents, we're using our engineering notation. So that's going to be the angle equals tan to the minus 1 of our J imaginary divided by our real. So we can convert between our Cartesian and our polar very, very easily. We can go that way very, very easily. Going back the other way is just as simple. Right? Just as simple. I will tell you as well, sorry, if you look in the link below, I will put a link to these notes as well. I'll scan them in and you can have these set of notes in front of you as we go along. So to go in the opposite direction, to go from the polar to Cartesian, what we would do is we'd say, well, actually, we've got our triangle. Let's relate this back to trig. Let's relate this back to something that we know. There should be a right angle triangle. I do apologise, I'm drawing this freehand. And we're going to say, well, actually, we've got this angle here, and we've got our value of z. We've got our hypotenuse. All right. And what we need to find is our opposite, which is our j imaginary, and our adjacent, which is our real. Okay. So to go from polar to Cartesian, what we do is we say, well, we've got our hypotenuse and we've got an angle. We must need to do something with that. So to find out our adjacent, what we say is that it's the adjacent is cosine of the angle times by our hypotenuse. And our opposite is sine of the angle times by the hypotenuse. Now, because you're going to be doing both of these, because you're going to want to find your imaginary and your real, what I would advise to do is when you're using a Casio calculator, pop this top line in the calculator, well, the line I'm going to show you next actually, which has the engineering speaking, but then all you've got to do is use the backwards button and delete the cosine and replace it with the sine and press equals, because all the numbers are exactly the same apart from the two functions there. Okay. So remember, we're not looking for adjacent and opposite. We're looking for our j imaginary and our real, which are exactly the same values. It just so happens that we use different words in engineering. So remember, our adjacent is our real, and that is cosine of our angle times by, and it's not hypotenuse this time, we're going to use z. Okay, and our imaginary, which is our j imaginary, is sine of the angle times by z. Now, if you remember, all we need to do is put the first line in and then tab back on our calculator and just delete the cosine and replace it with sine, and that'll spit that out. So you don't have to go rewriting it again. Remember, engineers are two things. We tend to be quite clever, but we also tend to be quite lazy as well. So we find efficient ways of doing things. Yeah, so that's the way that we convert backwards. So to go in one direction from Cartesian to polar, we use Pythagoras' theorem. And to go from polar back to Cartesian, we just use some basic trigonometry. So what I'll do is I will put these on the next sheet as a equation sheet, and then I'll upload that as well. Right. Now, that was a bit of a recap. What I want to do now is I want to explain to you how to do some basic maths with this. So there's two things that we're going to need to do. Well, there's four functions really. We're going to want to multiply, divide, add, and subtract. Okay? Now, when we're dealing with polar and Cartesian, there's a set of rules that you use for each one of these. And the way I've always done this is, whenever you're doing multiplication or division, always do that in polar. Okay? And the divide, always do that in polar. Okay? You add and subtract, always do these Cartesian and also in Cartesian. So multiply and divide in polar, add and subtract in Cartesian. And the rules are, for this one, so we'll do multiplying first. So do multiplication first. So we'll take our A at an angle of B, for instance. That's our polar value there. And we want to multiply that by C at an angle of D. Okay. Now the rule here is, okay, this thing here is called the scalar, and this thing here is the angle. So scalar, angle. And what we want to do is, we want to multiply the scalars and add the angles, right? So it will look something like this. I tend to use brackets with this, but I'm not quite sure if that's mathematically correct. I do A times by C at an angle of B plus D, like that. And that will give me the total answer for that. If we're going to do division, it's the opposite way around. So say we've got our A at an angle of B, divided by C at an angle of D. This time what we want to do is, we want to divide the scalars and take away the angles. It's just the complete opposite functions of what you did before. So this would now look like A over C at an angle of B minus D, like that. So divide the scalars, take away the angles. And the way that I remember which way around this is, if we're doing multiplication, to know to add the angles, the multiplication sign looks like an add sign, doesn't it? Just turned on its side. And on the division, to know it's a take away sign, well, the take away sign looks like the divide sign, doesn't it? It's got the line through. So that's the way that I remember that. Now, if we're going to add functions together, remember, we must do this in Cartesian. So if we've got A plus JB as one function, and I want to add that to C plus JD, well, what we do is here, the rule states that we add the real and then add the imaginary together. So the reals get added together and put to one side, and the imaginaries get put together and put to one side. So we'll do A plus C plus JB plus D, like that. Now this gets a little bit messy. This isn't as simple as doing the addition in division. It does get a little bit messy, so I'm going to give you an example with some numbers here. So say for instance I've got 6 plus J10, and I want to add that to 5 plus J20. Well, I add my reals together, so 6 and 5 gives me 11, and then I add my imaginaries together, 10 and 20 give me 30. So the answer to that would be 11 plus J30 for the addition. And finally, let's get squared up there. Finally, we'll do the subtraction. I just need to get my focus card as it's gone slightly out of focus. There we go. And we're going to do subtraction. Okay. Now, again, subtraction, remember, we do that in Cartesian as well. So if we've got A plus JB, take away C plus JD, well, what we do there is we do the exact opposite. We do the real, take away the real. Sorry. yeah, you take away the reals and take away the imaginaries. So what we're going to do here is, we'll say, well, it's A minus C plus J B minus D, like that. Now I'll put some numbers in here, again, for a bit of context, because that does look quite messy and it does look a little bit like you don't know what's going on. So, say for instance we've got, we'll use our numbers from before, which I'll just find them. So if we've got 6 plus J10, we want to take that away from 5 plus J20, then what we do is, we say, well, it's 6 take away 5, so 6 take away 5 will give us 1, plus J, 10 take away 20 will give us minus 10. So this plus here becomes a minus, and that becomes minus 10. So it's 1 minus 10J. Okay. Now, where does this become useful? Well, I'm going to stop the video just now because I am going to run into a slightly different topic. But what we're going to be doing is, with this particular bit of maths, is we're going to be looking at having resistors and inductors in parallel with another series resistor and inductor, or it could be a resistor and a capacitor. Now, these two things here are in parallel, and these two are in series, but we know that we can't just add a real to an imaginary number. Remember, our XL is our imaginary and our real is our resistor. We can't just add these together. So what we've got to do is, we've got to convert these over so that this thing here becomes a Z and this thing here becomes a Z. So the equivalent circuit for this one would be Z1 and Z2. Remember, all we do is a bit of Pythagoras' theorem, so we'll call this one R1 and R2. To convert over to Z1 is the square root of R1 squared plus XL1 squared. And Z2 is our R2 squared plus our XL2 squared. And the angles, remember this is going to have an angle associated with it. Our angles are tan minus 1 of our XL1 over our R1, which is our imaginary over our real. And our angle 2 is tan to minus 1 of our XL2, which is our imaginary, over our R2, which is our real. So we'll get our Z values and our angle values from that. Now, remember, when we talked about, if you're one of the students that were in my class watching this anyway, we talked about equivalent circuits, and what we said was that an equivalent circuit is the most basic form that a circuit can take. And normally, an equivalent circuit only has one source of power. In this case, I'm going to draw a battery, 2 wires, and one source of load. Yeah, or R in this case. Yeah, one source of voltage, or some sort of potential difference, some form of current flowing through 2 wires, and some form of load in the form of some sort of resistance, reactance, or impedance, right? So this could be R, this could be X, this could be Z. All right. So bring this back. This circuit here contains more than just 2 wires. It contains more than just 2 sources of resistance, reactance, or impedance. And of course, this would have been connected to a power supply. So what we need to do is we need to get these down to one source of impedance. Now, if this was a set of resistors, for instance, and I had say R1 and R2, like that. Because there's two resistors in parallel there, we can use something called product over sum. Yeah. And what that says is that product over sum, to get the equivalent circuit, which in this case would be simply RT. Okay. To get the equivalent circuit, RT is equal to R1 times by R2 divided by R1 plus R2. Right? So we multiply those two together, we add them together, and then we divide. But we don't have resistors, do we? Remember? We've got sources of impedance, which work the same, they act exactly the same in AC circuits as resistors, near enough. They work to resist the flow of current. So we can still use this equation here, but we're going to have to change it slightly. All right? So let's have a look and see what we've got. So we've got Z1 and Z2. Again, that's at an angle of θ1, and that's at an angle of θ2. Okay. So what we're going to do is we need to use our product over sum, same as before. Remember, it was R1 times R2 divided by R1 plus R2. But we don't have R's, we've got Z's, and Z's have complex parts to them. So our equivalent circuit is still going to be the same. It's still going to be one source of Z, ZT at an angle of θt. Yeah. And our ZT is going to be Z1 times by Z2 divided by Z1 plus Z2. And our angle will come from this here. But remember what we said, we've got impedances here, we've got polar notation. And if we're going to multiply polar, if we're going to multiply any complex number, we do it in polar, right? So the top bit, we do that in polar. And when we add together, remember, any addition or subtraction we do in Cartesian. So the bottom must be done in Cartesian. And then once you've got these two together, you convert your Cartesian back to polar because you're going to do a division. And remember, division is always done in polar. So we'll divide our Z1 times Z2 by our Z1 plus Z2. But this will be in polar form, this will be in polar form when we'll do the division. And that will be what the next video shows.